Welcome to this fourth session of today's symposium. It's a pleasure to be here and sharing this session together with Margaret Duff. So she's going to be the one doing the last two speakers, and I will do the first two speakers. And the first one is already very eager to start. That's Simon Arridge. So Simon has graduated in physics from Cambridge and then medical physics, completed a PhD in that area. Subsequently, so he's currently a professor in image processing and a visiting professor in a number of institutions in Europe as well as elsewhere, so quite a good scholar in this field. He has published hundreds of hundreds of papers on reconstruction. This is me thinking about PET all the time. And his presentation, some of that is on PET. And his presentation today is on inverse problems in radiative transport. Over to you, Simon.
Well, thank you very much for the introduction, and thanks for the invitation. I must say, it was really, really nice symposium. Lots of old friends that I recognise, and lots of new stuff. So I'm going to talk. Yeah, this might seem as a moderately cryptic title, because you may think you don't know what radiative transport is or why we're interested in it. But actually, you should recognise quite a lot of what I'm going to talk about. So it's to do with imaging with photons. So probably most of this audience interested in emission tomography, PET and SPEC, but photons are also used in various optical imaging modalities. And I will, there is a connection to the topic of the symposium because we're going to use, I'm going to get to how to use stochastic methods, which we heard about, fortunately, just before the break. And of course, so many of these, the algorithms there are borrowing methods from machine learning. Or to put it another way, machine learning has sort of activated interest in stochastic algorithms, and we can benefit from what goes on in them. So let's see what we're doing. Contrary to what might normally happen, I sort of put some acknowledgements at the start because I've worked with so many people and there's a lot of different people contributing to various things, and I just listed here the ones that are sort of mainly have contributed to this, so apologies if I left anyone out. Okay, so what are we talking about? So we want to do, so if you're going to do, if your measurement is the measurement of photons, and you want to do an inverse problem, I was always taught if you want to solve an inverse problem, you have to solve a forward problem, or at least you have to understand the forward problem. So what are the models for photon propagation? Well, they end up to be quite complex. Of course, the simplest, photons in empty space, no absorption scattering, is just a transportation, just a ray. But when you bring attenuation, either absorption or scattering into play, there's a really large range of these models. And actually, to be a very general solution, you can bring to bear typical methods like finite elements, finite volumes, boundary element methods, finite difference methods. But they can rapidly become really expensive to solve. And another point about them, it actually pertains a bit to the previous talk. Any numerical model usually has some systematic error, or modeling error, or what we might call epistemic error, which means that they are biased, just the forward model. On the other hand, there's classes of stochastic model that are sort of arbitrarily accurate, in the sense that they converge to an exact solution at the limit of infinite number of samples, which of course is not possible, but they are unbiased. So they will have mean around the true solution, but they may have high variance. So what I want to talk about is, I want to talk about nonlinear problems in photon-based inverse problems. And I want to talk about three things. So the heart of it is Monte Carlo, which is, of course, we all know Monte Carlo means many different things, but in this sense, we're mainly talking about Monte Carlo as a forward model. And we want to talk about adjoint Monte Carlo, which is not so commonly discussed as just forward Monte Carlo. And a new development which we call radiance Monte Carlo, which I'm going to explain. And then how these pertain, how we can use these in stochastic gradient methods. All right, so let's have a look. So let's just look at photon propagation. So what is this radiative transfer equation? Well, as I mentioned, it's this term comes up in optics, atmospheric physics, and such like, as a description of propagation of light, considered as particles, so not waves and not any coherence effects. In the nuclear physics, I didn't write it there. In the nuclear physics domain, it's more often known as Boltzmann transport equation. There are some differences, but it's essentially a balance. It's a phenomenological result. It's just a balance equation. And in the, as I mentioned, in the absence of scattering absorption, we can just propagate light along rays. So if we have a ray direction, S hat, just an element on the sphere, L is a distance along it, and R is what is the starting point. Then we just have the intensity propagating, transporting along the ray. That's very simple. But actually, this can be written in differential form, because as a single ordinary derivative, ordinary differential equation, with just transportation, the gradient of something we're going to call radiance along this direction. So this radiance is a photon density. It describes the density of all photons at any point in space as a function of angle. So it's a sort of in a 5-dimensional phase space. And we also, now we introduce attenuation. So if we look at this equation, there's no scattering. It has a simple solution. We call this a transportation operator. And of course, it's solved, it's an ODE, so it's solved by integrating along the line. So this is what's known as Beer-Lambert law. It says that if you have a starting point phi 0 intensity, and we go a distance along a ray, we attenuate the ray by the exponential of the integral along the ray. And of course, if we take the log of this, we arrive at a nice linear problem, the ray transform, which is just the integral along a line. And this is, of course, the basis of CT. Now, if we introduce scattering, it gets a bit more complex, because now, I know, so in the emission tomography community, we learned this from Chris. We talk about attenuation. And attenuation generally means photons taken away from the ray. And the predominant mechanism is scattering, right? I mean, there are, photoelectric effect which just kills photons, and Compton effect, yeah. It's like scatters photons with a change in energy. But from our, this point of view, we're not going to consider change in energy to complicate things a bit. It looks like, so this is the same equation, so far so good. We just have identified 2 terms at absorption and scattering. But now the point is we have another term, which this is a sort of sometimes called a rescattering operator. Now, if you just measure photons along a collimated line, we don't think about this much, and if scattering is weak, it doesn't contribute much. This represents photons that scatter a bit and re-enter the same direction, which obviously, in weak scattering doesn't happen very much, but the stronger the scattering, the more it happens. So if we measure along a certain direction, we actually can't distinguish between photons, so-called ballistic photons, that just propagate along the line, and those that have gone a longer path, except for the fact they'll have a longer time, and they may have a different energy. But from a mathematical point of view, what we've added now is, instead of T transportation phi equals a source, we're subtracting, and we call this a scattering operator. It's a local operator, it just redirects photons from one direction to another. Now, this has been known a long time, and if you think about inverting something, A minus B, you might think of a Neumann series, and you'd be right, because if you do some not so straightforward, but mathematically sound steps, you can arrive at something that looks like it was called method of successive approximation by Sobolev, but it also is a Neumann series. In some sense, it's also what's often called a Born series. But here's the point of it. It says that the density of photons at some point in space is the propagation term. So this is what we call the unscattered photons, the ballistic photons, they're also called. So this is just the photons that propagate from the source. Then we have photons that propagate once and are scattered into another direction and propagate again. but that can repeat it as many times as make physical sense, and from a physical point of view, this will converge if there's any attenuation at all, because they will contribute less and less. But let's thinking of the first two terms. This is what you might call a radon transistor. Sometimes I use the term broken ray transform to say you propagate to a point, scatter, and propagate away from that point. And perhaps I don't need to mention this too much. Also, these terms collided, uncollided, and collided. That comes from the nuclear physics industry. So the Boltzmann equation, a lot of this research was done in the 40s, 50s, 60s, from the dawning of the age of nuclear physics. All right, but without going, because we don't have so much time, let's talk about what we mean by Monte Carlo. So Monte Carlo means that we abandon trying to do any kind of solution based on meshes and variational principles. We simply propagate photons. We literally reproduce this series. We propagate photons at random distance. So to determine this scatter point, we say, well, we now interpret this as a probability distribution. And we say, this initial photon will be drawn from this distribution to predict the length at which it survives before it's rescattered. Then we pick another direction to scatter it, and then we...
Back on full screen, sorry.
Oh, sorry, I beg your pardon, yes. Should have mentioned that, sorry. And then we rescatter it and propagate again. Now that's what's called Monte Carlo method, and it looks like this. So if we only have a very few photons, we don't see much. And then if we have more photons, we start to see some things appear. And then after a certain amount of photons, we see what we might expect, this so-called uncollided part. That's just an exponential decay. And then this part here, which represents all the photons that got through multiple paths. So the point about this model is, it's very popular, it's very, very simple to program, it's massively parallel, and maybe we can discuss this later. There's now lots of interest because there's there's some what are called ultra-fast Monte Carlo models exploiting GPUs. So it becomes, although it's been known for a long time, it was a bit academic because it was quite painful to use. But nowadays it can become very fast. But it's still, to get a sort of accurate solution, you still need a lot of photons. So let's just mention about this adjoint stuff. So the basic principle is, if we think of this as a propagator, you can also think of it as a Green's function. So we start at a position R naught in a direction S naught, and look at what we get at another position R in direction S at. The basic physics tells you that that's the same as starting at R in the backward direction and seeing what photons arrive back in the backward direction. And if you integrate over the source, you arrive at an isotropic source, such as we get in emission tomography usually. This says that the radiance due to an isotropic source at R and S is got by propagating backwards, starting at R in the direction you were measuring, the collimation direction, if you like, and looking at all the photons, irrespective, just integrating over the directions at the point R0. So this is the basic principle behind what we might call adjoint Monte Carlo. I'm going to skip a few bits. I'm probably going to be slow. What's the time? Okay. This is what radiance Monte Carlo can do. So without going into too many details, I'm launching photons at various points in the domain. Like at this point, this is an isotropic source. It's discretized somehow just to measure it, but let's not worry about that. And so the adjoint source looks the same, but in other points, we get very directional information. So at this point, there's a very directed radiance in this direction, but the adjoint is backwards. This is just a sort of taster to explain that this adjoint Monte Carlo has an intuition that's correct. Okay, let's just quickly mention how does this got to do with reconstruction? So a classical way would be to go to deterministic methods. So deterministic method, again, apologize, it won't be too much of this, but the abstract model of photopropagation, we call it AX, it's got by solving the PDE, the transport equation, for some source. And then we'll include, there's a nonlinearity because that arises in some modalities, which we call hybrid imaging or coupled physics imaging, which I'll show an example of that later. And then M is just the detector. So now we do the normal thing. We set up a cost function. Let's keep it simple and call it L2. And then we want the derivative. So this tells you that we want the inner product of the data residual with the linearization of the forward model. And of course, when we want to do adjoints, what do? We take terms from the right to the left and adjoint them to get back propagation. And if you do this, again, let's not worry too much about all this detail, but we have to solve an adjoint Monte Carlo, an adjoint transport equation. And we take the data residual, we back propagate it, or we take the adjoint of the measurement, so we redistribute it in the directions that it was measured in, and solve the back propagation. Now, if we do all this, we end up with some expression. So this is purely based on the PDE analysis. It tells us that the local change, for example, in absorption is just given by the inner product of the forward propagation and the back propagation, whereas the change in scattering is slightly more complex. So what am I saying this for? So one way you can proceed is to build a solver for L and a solver for L star, and then construct these things, and then use a gradient-based method. So now let's see what is this to do with, where does stochasticity come in? So, as we say, the classic way we would have an expensive forward model. But Monte Carlo is arbitrarily accurate, even though it's not strictly an operator. We can't put it into a variational setting. It's just giving particle numbers, so you can't put it into particular Banach spaces. But what we proposed is just to use Monte Carlo as a proxy for the deterministic RTE and just solve the forward and solve the adjoint. Now, if we do this with a very large number of photons, we get an accurate estimate of the gradient, but this is quite expensive. So the new idea, so this is where we borrow a bit from a couple of the previous talks, or connect it to them, let's say. If we use very few photons, we get an inaccurate model, but it's unbiased because the Monte Carlo is unbiased. And then we simply use or leverage techniques developed in machine learning for adaptive stochastic gradient descent. I mentioned there's something called MCQ, which is Monte Carlo Markov chain Monte Carlo, which is a posterior sampling idea, which is related. So we've seen this a bit already. A deterministic model, we take a gradient step by taking the gradient of the full objective function. And in the stochastic setting, we take a subset, and we believe that in expectation over the samples, the subsets equal the true objective function, and the same for the gradient. Now, what we've seen previously is that we somehow have to choose the subset. So this is a big topic, right? It's choosing subsets randomly or through a prescriptive recipe. In the machine learning, of course, we would call this batch gradient descent, and this is what we call mini-batch gradient descent. But the key idea is Monte Carlo, we're not exactly taking a subset of the data. We're saying that Monte Carlo, you say run 10 to the 6 photons, and then we run another 100 models with 10 to the 4 each. Each of those 10 to the 4 acts as a mini batch of the 10 to 6, but it's not correlated exactly. It's not at those photons. We're not running those individual photons back. We're saying that they're drawn from the same probability distribution. All right, and then we know, I guess people here are somewhat familiar with adaptive gradient descent. When you're using subsets, we know that we don't iterate to the correct solution. We might get to a limit cycle. And the techniques we can use is either to reduce the step size at each iteration or increase the sample size. So the first one is the same as normal. Increasing the sample size means just running more photons throughout the algorithm. And then, well, there are a couple of tests that you can take to estimate at which point you should change the recipe. So because I'm probably taking a bit too long, so let's look figuratively. If we're running a very high resolution model, we can take deterministic steps to converge to a solution. If we take a low resolution model here means low photon count model. We are taking some sort of random walk, and we may not get to the solution, although we might get a conditional mean estimate. And then here what we're saying, because I can't draw the picture exactly, but we adapt the step size and all the sample size. Okay. So the algorithm, so what I'm going to show you, what we do is we fix what we call the photon budget in the inverse problem to be the same as the number of photons to run one forward model. So if we run 10 to the 6 photons to create data, we're going to partition in the inverse over iteration, and the total will be the same. So the cost of running the entire inverse algorithm will be the same as one forward step. And again, I think in the interest of time, I won't go through all of this details of this algorithm. Let's look at a couple of cases. This is called photoacoustic imaging. This is a hybrid modality. You shine a light on something, the light is absorbed and creates, it's a pulsing light, so it creates a shock wave which outputs a spherical wave that's detected. So we detect the distance from the detector because we get the time of the flight of the acoustic signal. So this has been around 20, 30 years now. So we partition our budget. We use half for the forward model and half for the adjoint model at each iteration. And then we have a number of possible choices for this adaptation. Again, perhaps I should skip a bit through this. We can fix the step size and adapt the sample size, or we can adapt them this is based on the variance in different ways. Let's, again, not dwell on that. So now, this is some results. So what do we see here? So on the right, this is a one-dimensional problem, so it's radially symmetric. This is the solution with the yellow is the solution we want, the black is the solution we want to find. And these are these three strategies. So they have different rates. So strategy 3 is better. And here, this is the fit to data. But let me skip to, because I think the time's running out. Let's skip to an animation. So now, same thing. So on the left is the data. On the right is the true solution. And we're going to start, so let's just step it piecewise for a moment. So we start with very few photons, 200. We don't get very good solution, and then as we iterate through, there it jumped. It decided to put more photons in, and if I now run it as a movie, it iterates through, and then at some point, if you look at the top title at the top right, it will jump up. It decides that it's getting closer to convergence. It wants to increase the sample size, so increase the number of photons. And so on, and it goes through to some kind of convergence. But what I want to say is that the total number of photons put into the system is fixed between these different strands. So if I go back one, this may make more sense now. These different strategies. So we have the sample size. So in the first strategy, sorry, which one? Strategy 2, I think it's maybe mislabeled. There's no change in the sample size. Strategy 1 and 2, we increase the sample size. And here the step size. Strategy 1, there's no change in the step size, and the others we're decreasing the step size. So you'll notice there's a lot of stochasticity, but this is what we expect in a stochastic algorithm. Okay, so so now let's remind us that so to do in 2D, we need this radiance Monte Carlo, so there's that picture again. And next, because I think we didn't start quite on time, but let me get to the end. This is now 2D version, the same thing. So now we see a few things. So one thing you can look at is the model. In the first iteration, this will cycle through. So in the first iteration, we're using a very small number of photons. So this is written, this number is up here in the few thousands of photons. So there we're only using 80, 90, 100 photons. So you see the rays individually. This is what the data looks like. This is, again, this photoacoustic problem. And this is the reconstruction, and this is the reconstruction error. So it has a stochastic descent, as you would expect. And that's a final iteration. So this is not, of course, by any means perfect. So here we have the two parameters, the absorption and the scattering, and the final recon, and the recon error from this stochastic process. And here's a second problem. This is optical tomography. So this is a transmission problem where you measure photons propagated through the domain and measure on the boundary. And again, we're having some plausible reconstruction. I mean, there's plenty of, it's a very highly ill-posed problem, so this kind of artifact is not unexpected. But we are using here only 10 to the 4 photons in the initial step, and then increasing this. Okay, and this with more photons. Oh, sorry, yeah. That previous one was fixing at singles. Yeah, sorry, this was fixing at 10 to 4 photons. Here we have we're increasing from 510 to 1 million per iteration. Okay, let's stop there. So what I've talked about is giving you some ideas about inverse problems on radiative transport, and there are many methods of modeling, but I've concentrated on stochastic models because they have this arbitrary accuracy, and they lead to what we call the fully stochastic inversion. So, you know, there's plenty of things we're working on here. So these were noise-free in the sense that, I mean, the data is noisy because it's stochastic data, but we computed the data with very high number of photons. So we didn't include any explicit regularization or early stopping. Also, this L2 distance is not really the correct one. Of course, we would think of Kullback-Leiber as a difference of distributions, but since we have just sets of particles, we probably should consider Wasserstein distance as well. And then when we are in this adaptive subsampling, there are many, you know, as we heard a couple of talks ago, there's a long list of adaptive subsampling schemes like SAG, Sarah, SAG, and so on. I didn't mention we need to, ideally we know the Lipschitz coefficient, the forward problem. How do you estimate that for stochastic forward problems? Don't really know. We could include preconditioning, we didn't. And in theory, we can build this into a posterior sampling because it's stochastic. One point to remember is that by doing this, we've estimated the map, and because there's no regularization, actually maximum likelihood. In theory, you could take like in any Monte Carlo, you could average over the last few elements of the chain to get a posterior conditional mean. But because it's nonlinear, that would be a slightly biased estimate. So if you wanted to do it, we would need to get to the endpoint, then just resample from the posterior. But that's, I mean, it's not as cheap as we would like, but it's eminently doable. Okay, so I think I'll stop there because it must be time. Thank you.